Wording so much is
being late, right for you. I would say
cool. It's pretty cool. Yeah, I wanted to actually, so I looked at some pictures. You guys keep saying it's papers that you guys
Om alla hänger med, men är det bara så kvar så är det ju
Did you guys say that you leading up to it, you say that you guys
So maybe there is something.
I was thinking of something here. I can also simply sit here.
Or you can transfer you. Yeah.
We wanted this place already earlier, so I think Andre.
No, he said you can push it.
Oh, okay. Well, I'm sure it will be. Yeah, but I think that's sort of finished by now. I looked when I got the camera. She was there. I'm sure she'll present
There is an issue.
So before we get started, two quick announcements. Tomorrow's morning talk will actually be the theory seminar by Christiane, which starts at 11 and it's in the other building. It's FB52 and well, for those who don't know where it is, just follow the crowd to guide you guys there. Then also tomorrow in the evening we have a buffet, which starts at 6:30 and that's down in where the lunch place is in the other building. And you can also just follow the crowd. So that's 6:30 tomorrow. And now I'll give the floor to Dimitri, who will talk about electronic Mach-Zehnder interferometer in the interview from all.
Thank you very much to organizers for inviting me to see Stockholm. Never been before. I'd like to take care of a very nice conference. So today I'll talk about electronic Mach-Zehnder interferometers in the integer quantum Hall effect regime. So I will not touch fractional quantum Hall effect interferometers. So this work was done in collaboration with John Chalker, from whom I learned a lot. Some of you probably saw parts of this talk, but there are some more new and interesting results. I think they'll talk about it. The outline of the talk is the following. I'll give an introduction where I talk about what is Mach-Zehnder interferometer, and standard Mach-Zehnder interferometers are kind of optics. And I'll talk about them. Then I talk about important ingredients of electronic Mach-Zehnder interferometers, namely Aronoff-Bohm effect, then one-dimensional electron gas, which is used to create these interferometers, and quantum point contacts, which serve as beam splitters in these experiments. I'll talk about experiments with Mach-Zehnder interferometers which were done recently, about some interesting effects which were observed in some puzzles which were observed in these experiments, which I will try to explain. So I'll present my theory of this to explain these puzzles. And so basically this theory is based on inclusion of electron interactions, and in particular long-range electron interactions. And I'll give some simple physical picture, which is made to explain it, just some fingers basically, and I'll show exactly solved model. I show how to solve this model, and I show results of this solution. So this Ernst Mach, who invented Mach-Zehnder interferometer. There's no picture of Zehnder. So we have a source of coherent light. Then there is a beam splitter. It's basically half-silver mirror. There is another mirror here, and then there is another beam splitter. So when light enters this beam splitter, if you go along this path, here light will have pi shift. Here it also gets pi shift. Then it doesn't get pi shift when it's reflected from this mirror. It's going here, or it either doesn't get any pi shift when it goes through the half-silver mirror here. And the same for this light. So it doesn't get any phase shift, apart from small phase shift from this slab of glass. And then there is another pi shift, and there is another pi shift here. So let's see. Let's take this beam. There is no phase shift, pi shift, pi shift. So there's zero phase shift. Then if you take this one, pi shift, 0. So they come with the same phase shift, and it gives you the total current or intensity, which is equal to this intensity. And if you follow along this path, you have different phase shifts from these two lights, and one is coming with pi shift, and as a result, pi shift, and you get 0 here. So the total current is equal to current here, or intensity rather, in this case. And if you put some sample on the path of the light, you can measure these phase shifts, which appears from this due to this sample. And this was the idea to use in electronic Mach-Zehnder interferometers. But initially, people tried to use quantum wires, and in quantum wires there is a very strong backscattering, and it's very difficult to implement because current is not conserved. But then people decided to use electrons in quantum Hall effect regime. But there are some other components of these interferometers which I try to explain. So first important component is Aronoff-Bohm effect. So Bohm effect appears when you have, for example, magnetic flux, and you take electron and circle around magnetic flux, and this electron will obtain some phase shift. It was predicted by Ron Bohm in 1959 and supported by experiments by Chambers in 1960. So the phase shift will be equal to flux quantum, number of flux quantum multiplied by 2 pi. So second important ingredient of these interferometers is basically these are H states of the quantum Hall H states in integer quantum Hall effect regime. So if you have a two-dimensional semiconductor in a perpendicular magnetic field at the edge of the sample, you have the electrons will develop cyclotron orbits, and at the edge of the sample you have cyclotron orbits circling like that. So you have current in this direction, and you have current in this direction. And because these edges are spatially separated, the scattering is strongly suppressed, and you have an output of coherent light source in terms of electrons. And here is a picture of these H states, how they appear. So you have Landau levels. These Landau levels are modified by potential at the edge of the sample. There is a gap between different Landau levels. So if you look at the wave functions in the lowest Landau level, as we saw many talks here, wave function depends on coordinate in this direction and coordinate in this direction. So it's plane waves. You have plane waves, if I can here, so plane waves in y direction, and is Gaussian in x direction. This type of shape. Of course, this overlaps strongly if magnetic length is very small. Yes. So now, if you look at the electrons, so if you put electrons in every of these states, you have integer quantum Hall insulator, because you can't put more electrons on top of it. And then at the edge of the sample, electrons can hop from one state to another state. And quantization of this hopping will give you so this comes from linearization of the external potential at the edge of the sample. So you basically have electrons with linear dispersion at the edge. There's a difference. And the important thing is that electrons from this edge don't hop to this edge. Another important ingredient of interferometers is quantum point contacts. So you need to make somehow beam splitters. And to make beam splitters for electrons, you just take these two H states. You take this quantum Hall bar, and then you apply voltage here, and you apply voltage here. And then it will modify the path of the electrons like that, and electrons now can like scatter. You have a source of electrons. They follow this path, and due to this voltage here, you can jump to another wire, and you can measure current. So here you have two different chemical potentials, mu1 and mu2, and so like it's shown here, and electrons can channel with some probability, say t, or they can tunnel here is probability t, and they can reflect this as probability 1 minus with probability 1 minus t squared, and you have non-equilibrium distribution of electrons in this wire. So all states below this energy are occupied, and these states are occupied with some probability. It depends on the tunneling in the contact.
Are they moving in the same direction on both edges?
Yes, so here they're moving in the same direction, and I'll show you why. So for Mach-Zehnder interferometer, you really need electrons moving in the same direction. And in quantum Hall bar, electrons are moving in these directions, yes. But then you can imagine that you can connect them like that, and I'll show how to do the experiment. So if you unwrap this picture, you see that electrons are moving in the same direction. Actually. So this was done in an experiment with integer quantum Hall. You see here is two-dimensional semiconductor, and it's in perpendicular magnetic field. So here you have quantum Hall bar, the edges are moving in different directions, but then you can make a hole in this semiconductor. And then if you add two tunneling contacts here and here, you'll see that electron can take this path, or it can jump and take this path. And then there are two sources and two drains. So these sources and drains are at zero chemical potential, so they're grounded, and electrons from this source. And of course, there's a magnetic field coming through this semiconductor, which gives you Aronoff bomb phase shifts where electrons encircle. This was experimentally realized in 2003. And these are parameters of interferometry magnetic field by Tesla.
So you say at the end you have point contacts?
Yeah, these are just point contacts. So these are point contacts. Okay, and these electrodes are made to change the length of the arms. So if you add some contact here and apply voltage, then electrons will. So if you add voltage, electrons will go like that, which will effectively change the length of the arm, and it will also modify the area of the interferometer, and it will change total flux coming through the area. Then you can see the changes in the Aronoff bomb interference picture. And so people looked at the interference. So you should expect to have Aronoff bomb fringes like that. And so what to change in this system is here is time. So it's very difficult to change the number of flux coming through the interferometer. So what they do, they just short circuit the solenoid, which produces magnetic flux. And then the current in this solenoid decays very slowly this time, so it's 1 flux current per 50 minutes, and then if you wait long enough, you will have Aronoff bomb oscillations in the current. Or alternatively, they can also change, gate voltage at this contact, modifying the total flux coming through the array. So they see perfect Aronoff bomb oscillations here. But then they decided to look in the, so this was done for very small voltages, and then they also can look at larger voltages. So this source DC bias is voltage which is applied to voltage between this source and this drain. Okay, so they change voltage and they look, so in this direction, they should, it's gate voltage, it's voltage here. And in this direction is source bias. So if I draw interferometer, so we have contact here with source 1, source 2, and flux here, 5. There are two contacts. Okay, and there is chemical potential mu1 and mu2, and this gate bias is basically mu1 minus mu2. Okay, so there is a non-equilibrium distribution of electrons. This way. It's coming from these electrons here, and it's coming from electrons which have larger chemical potential. So what they see along this line, they should observe Aronoff bomb interference like that. But here they observe very interesting pattern. They saw that if you change source bias, then visibility. So first I need to define visibility, of course. So visibility is defined as the maximum conductance minus minimum conductance divided by maximum plus minimum, which is basically the amplitude of the Aronoff bomb oscillations which you will see. If the system of electrons is non-interacting, or there is only one electron in this system, then you should have constant visibility. It should be equal to 1 if there is no any source of decoherence. But in these systems, you saw that visibility started to decay with energy, basically with source bias. But what is more interesting, it reappeared again, and then it decayed again and reappeared. So if there is, if you expect that there is some decoherence, probably you should see something like just exponential decay, but they saw rather very peculiar picture. And more importantly, probably that the phase of the Aronoff bomb oscillation dropped by pi at these points. So the phase, by the phase I mean that if you have Aronoff bomb oscillation, some sine function shown here. So if you look at this function, then the function will decay with voltage, but then when it reappears, it will be shifted by pi. And it was very interesting observation, and experimentalists, so it was done by a group from Weizmann Institute, and in this paper already they proposed, they observed it in this paper first, they proposed that probably the reason for these oscillations in the visibility is a long-range nature of electron-electron interactions at the edge. Basically, if the edges are made not with the gates but by etching, then you wouldn't expect very strong screening of electron interactions, and this can play an important role. So, and afterwards, a similar picture was observed by a French group, here in 2007. Okay, so so in principle, if electron interactions are short range, then it scales again to non-interacting Fermi liquid, and you should be able to explain your system again with single particle picture, but then you can't explain this picture. So you should take into account something else, a long-range electron interaction or something different. So there are different approaches to study this problem theoretically. First, there was a paper by Sukharukov and Chiyanov, and he proposed that probably these oscillations, you say, is due to additional channel here, which is here. So he said that plasmons at these two edges interact. So there is some asymmetry involved. And due to this interaction, he calculated and showed that there will be oscillations in the visibility. But later on, experimenters ruled out this possibility, so they took a second edge and put it far, and they saw that oscillations in the visibility still exist. Then there was a paper by Cholker, Defen, and Millet in 2007. So they took a rather different approach. They say, okay, let's consider interferometer like that, but without any additional channels, and an integer quantum kovrizhin mu is equal to 1. So there is only one edge. And let's switch on long-range interactions. So they considered Coulomb interactions. And let's study interactions exactly using bosonization, but they studied tunneling contacts using perturbation theory. So they observed some decaying behavior of the visibility, and there are some non-trivial features, but they didn't see stable oscillations for the visibility, unfortunately. Then, afterwards, there was a paper by Levkivsky and Sukharukov. So they proposed another mechanism. They say that probably it's very important that experimentalists in most of the experiment, they say measure these random oscillations in visibility in mu is equal to 2 regime, although they didn't use second channels. And they say that these channels probably are important, and this is very similar to what Sukharukov proposed, to use additional channels as a resonator for plasmons. But this somehow is not general, and it would be interesting to see if you can have this property in just mu is equal to 1 regime. And recently, in 2008, 2 papers came, one from Neder, experimenters who did that experiment, and then there was another paper from Korean group. So they've taken this interferometer, but they approximated interactions here. It says that electron interact with constant interactions inside here, and they don't interact outside. But then they did many approximations which are very difficult to judge because they're not standard, and sort of mean-field approximations. And I'll explain later what is the consequences of approximations in this paper. And this paper is rather simple two-particle problem, which I also showed. Okay, so first of all, I would like to show a very simple physical picture of why this oscillation in the visibility would appear in the interferometer. And for that, I need to explain how the contacts work, and so how the phases work, and so on. So let's consider a single contact, for example, this one, and consider a single particle moving through this contact. So you have a probability of a particle to tunnel through the contact, say 1 over square root of 2. I assume that half of the particles tunnel through the contact here, and half of them tunnel to this channel here. So there is a probability 1 over square root of 2 here, the same probability 1 over square root of 2 here. Sorry? sorry, yes, you're right. Amplitude. The probability is equal to 1/2. Amplitude is equal to 1 over square root of 2. And there is a minus 1 over square root of 2. This minus is similar to pi phase shifts in the light interferometer. And this 1 over square root of 2 again. And then I introduce Aron-Bohm phase here, so which comes as a phase shift in this exponent. And then I can just calculate total amplitude, just summing up all the amplitudes with corresponding phase shifts. So here I have 1 over square root of 2, if I look at this picture. Here I have another 1 over square root of 2, and there is a phase shift by e to the I phi divided by 2. Here is the same, but the phase shift is minus I phi over 2. And the total amplitude is equal to plus phi over 2, and it just gives you a current which is oscillating function of the flux, which is just simple Aron-Bohm oscillation. Nothing interesting. But it's a way how to calculate it, it's simple two-particle or one-particle picture test. So now I modify this problem a little bit, and I consider a two-particle picture. And this picture will actually give us result of oscillating visibility, and I would like to explain carefully. So let's assume that there are two particles starting on this channel here, and then these particles can take all possible paths through the interferometer. And you can imagine it's like say spin system. You can have particle on the up channel or on the down channel here, and you can have particle on the up channel or the down channel here. If you multiply, so if you take all possible paths, you have 16 paths, and you can sum them up. And, so this is I'm going to do. So let's consider different. Let's separate it in two pieces. The first piece is when both of the particles go from this channel to lower channel, and also second part is when one particle propagates only on this channel, and another particle comes into this channel. And because the particles are especially separated in these edge states, I can consider them as distinguishable in principle. That's why I can draw these lines as blue and green. So there is a corresponding amplitudes, 1/4, 1/4. Then there is e to the I5. And importantly, I introduce interaction between particles when they are on the same arm as the interferometer. So these particles are on different arms. There is no phase shift due to interactions. And these particles on the same arms, there is a e to the minus iu tau, where tau is time of propagation, which is equal to length of the arm divided by d Fermi, and u is effective interaction between these particles. So there is phase shift due to interaction with these two particles, and there is another phase shift here due to interaction between these two particles, and there is Aron-Bohm, of course, here. So if the sum of all amplitudes for two particles to be transmitted from the upper channel to the down channel is this one, and then this corresponding amplitude for one particle to be transmitted and one particle to be transmitted to another channel. And if I sum up these two amplitudes, so it should be here.
Sorry, u here is being treated as a constant?
Sorry, what?
U
is just some constant interaction.
And same.
It's same on both channels, but in principle you can change it, vary it, and so on. You can modify this program and say, so it's just a toy model. So I'm going to explain exact solution, but it's a toy model to understand why these oscillations would appear, and you can explain it to any student or schoolboy. Very simple. So yeah, you can, in principle, you can start with n particle here and m particle here, and you can also sum up all the amplitudes, and you'll get some special function, hypergeometric function, but it doesn't give any new physics, so I'll better use the exact result afterwards. So what you get is a current, which is, so here is cos phi, as in previous problem, is just Aron-Bohm, but very interestingly here, cos phi is multiplied by cos u tau divided by h bar. So again, so interactions inside the particles interact with interaction u. Here is interaction u, but only when both particles are on the same channel. Okay, so this approximation was this formula. And this u doesn't depend on the distance between particles. I assume that there is some long-range interaction, like Coulomb, for example, which is on screen. You can do the same for interferometer with arbitrary tunneling here. And I should tell you that importantly in experiments, when they measured visibility and they saw this picture here. So this picture didn't depend very strongly on the tunneling in these contacts. So if they change tunneling here, they can modify it from 0 to 1. Or here, this picture didn't depend on the tunneling, and this picture didn't depend on the difference in the length of the arms. And for example, if you take one particle, if you calculate this phase for one particle problem, you should see a phase which goes linearly with energy. If there is a difference in the length of the arms, and the slope should be proportional to, so it should be V multiplied by the difference in the length of the arms, because of K Fermi there is a difference in phase on different contacts. So you can calculate the same two-particle problem for different tunneling amplitudes or tunneling probabilities here, and what you get current, which is also modulated by this prefactor. So visibility is visibility for non-interacting case multiplied by this prefactor, which is a oscillating function of u tau. So in two-particle problem, u is fixed, but you can imagine that there are many particles and there is some effective interaction between these particles when you change the voltage. So you have more particles at the same time inside the interferometer when you increase the voltage, and this gives you effectively stronger interaction and stronger phase shifts. And in principle, you can associate this u tau with this voltage for many particle problem and see that there will be oscillations in the visibility. And interestingly here is there's a T8RA. So you'll see that for different, for tunneling amplitudes or tunneling probabilities which are not equal to 1/2, we get not perfect oscillations, but oscillations will, so they'll not go to 0, but there are other to 0, there are go like that. So there are no perfect zeros for interferometers with different tunneling amplitudes in this picture. So how to solve this problem? This problem is quite difficult to solve because you have a system out of equilibrium and you have a system with long-range interaction, and there are no general methods to solve it, but we will attack it in a different way. So our model will be the same as I showed here. So we assume that electrons interact only inside the interferometer, but they can interact with arbitrary interactions, and they don't interact outside the interferometer. In principle, if there's interaction, so interactions between particles in this channel, for example, are not important because they don't change the current. Yes. So interactions here are also unimportant because of the Pauli blocking. What is important that there can be interaction between this and this particle, or interaction between this and this particle. Oh, of course, there can be interaction between this and this, but these are very far usually. These interactions are, in principle, important, and they can lead to second harmonic in Aron Bohm, which we calculated using perturbation theory. But for our exact solution, we will neglect this interaction. We only consider interactions inside the interferometer. And so this gives us possibility to consider these tunneling contacts as for non-interacting fermions. And so inside the contacts, particles are easily described by, so I mean the tunneling in the contacts is easily described by electrons, and the system inside the wires is better described in another basis or in the basis of plasmons, because then we have a quadratic Hamiltonian which you can diagonalize. So we want to combine these two approaches of electron description and plasmon description. So electron description will be good for tunneling, and plasmon description will be good for interactions inside. So plasmons are basically, if you have a field Fermi C, so you have electrons filling all levels, so you have linearized dispersion, and there are all states up to K Fermi are filled with electrons to minus infinity. Then plasmon is basically a superposition of particle Paul excitations is up to some momentum. And the wave function of the electron in plasmonization description can be this claim factor multiplied by exponent of all these plasmon excitations. It's no linear function of plasmon. Okay, so this is our model. We have two wires with chemical potentials μ1 and μ2. There is a flux coming through this plaquette. So there are two tunneling contacts. There are lengths arms T1 and T2, and there are interactions here in these two regions. So at the far left, the system is connected to the battery, so we assume the electrons are in thermodynamic equilibrium at these two chemical potentials. So the idea of the method is very simple. We start with two wires of electrons at different chemical potentials and without interactions. And at time t is equal to 0, we switch on both tunneling in the contacts and we switch on interactions. And then we look at the system after some time when the initial perturbation which was created by this switching on procedure will be washed away by the current of electrons, because the current is chiral. So everything which is created here, all excitations, will go away after some time. This time will be order of d divided by dk. The Hamiltonian is very simple, so you have kinetic energy, tunneling, and interactions. Kinetic energy is this one. So this psi is a Fermi operator at point x. There are two channels, 1 and 2, it's up and down. And then there is a tunneling, so you destroy a particle at position 0, you create a particle at position 0 at two different channels, and there is I alpha, which corresponds to Aron-Bohm phase shifts. And we consider some arbitrary interaction inside the interferometer, which is density-density interaction. So U of x prime can be any. We consider different cases: long interaction, short-range interaction, long interaction. So the operators can be written in terms of relation operators of electrons with momentum k and channel eta. These are standard commutation relations, and momentum is quantized as 2 pi over n. Yeah, so as I say, outline, I explained already how do we calculate. So we start at t is equal to 0, this system which is described by two field Fermi series, two chemical potentials. We switch on interaction and we switch on channeling, and then the wave function will evolve with this time-dependent exponent, time-ordered exponent, and the operators will evolve under this Hamiltonian H0. So the Fermi sea will be described as all states field from minus infinity to some value q, or q is the Fermi moment, which corresponds to the 1. Yes, so in Heisenberg representation, you can write any operator in this form, and we are interested in the current, and current can be calculated as a commutator between the Hamiltonian and number of particles on the upper channel. So it counts how many particles goes from the upper to down channel. What is important is how to connect operators, fermion operators, for single contact, for example. So if you have a single contact here, you can connect operators at the position x plus 0, so plus epsilon with operator minus epsilon by this very simple linear transformation. It's just because we consider non-interacting electrons in the contacts before the contact and just in the immediate vicinity after the contact. So there is this linear relation between electron operators before and after the contact. And this S is a scattering matrix, so basically R and T are reflection and channeling amplitudes, and this is a Aron-Bohm phases. And there's a formula for the current, so you can calculate the current, and you see that there are two contributions. One is incoherent contribution, and another is coherent contribution, which is proportional to a correlator of psi1 and psi2. And this quantity we are interested in, and this quantity we calculate. This is just bosonization dictionary. Maybe I don't want to talk too much about it. So you can always represent for non-interacting fermions with linear dispersion. You can bosonize these operators. You can write it in terms of boson operators. And these are plane factors. These are number operators. So bosonic operators is a superposition of plasmons with different momenta. These bosonic operators have these commutation relations. So the plane factors are Majorana fermions. Then you have BQs. So what is important is that you can, this exact identity between operators of fermions, creation and annihilation of operators is, of fermions with momenta k and index, channel index eta. And you can connect them with plasmon operators. So this exact identity you can prove it. And this will use afterwards. And particle number operator counts number of fermions in the channels. Here, in principle, one should regularize it and extract infinitely filled Fermi C, but not here. And the fermion density can be written in terms of a derivative of plasmon operator plus number operator. So one can write Bose-Einstein Hamiltonian, and what is important that in this Bose-Einstein Hamiltonian you see that kinetic energy and interaction energy becomes quadratic. So this Hamiltonian can be easily diagonalized. You can do it via Bogoliubov transformation, or you can write equations of motion for pi operators and you can solve it, and you also get the same result. And so here is diagonalized Hamiltonian. In our problem, we get additional contribution due to the number of operators, which is not very important at this point. So you can write your bosonic operators as contribution from 0 modes, and there is a contribution for plasma modes equal to 0. So you can, to find this APQ, BPQ coefficients in F, you need to solve system of Bogoliubov equations. But it's all not very important. What is important that at the end of the day, you see that in this formula you have plasmons, and these plasmons before. So this problem basically is for one-dimensional wire, which is disconnected from other wire, and the electrons interact only in this region. So you have non-interacting electrons here, you have non-interacting electrons here, so it x equal to 0. The non-interacting, and the plasmon wave function is proportional to e to the ikf. After the plasmon goes through this plasmon wave function, it will be multiplied by the phase shift, which is k-dependent. So here you see that before the contact, or before the interacting region, you have just plane wave, and then after the contact, you have plane wave modulated by delta E. So it's a E-dependent phase shift here. And this formula is a formula for phase shift, can be calculated for constant interactions. It's the same as I considered in two-particle problem. You just take U is equal to constant, which is an independent distance. But you can also do it for different potentials. It's basically you just need to solve a Bogoliubov equation for different type of potentials, and it can be solved almost analytically in the case of potential, which is G e to the minus x minus x prime alpha. So for this potential can be solved almost analytically. You don't need to solve Bogoliubov equations. So at the end of the day, you need to evaluate these matrix elements. The Fermi C is a non-interacting Fermi C here, so we can evaluate it. We know how does it look like. So in the Fermi C is just few, all the states which are few below mu1 and mu2, and it's represented by this formula. So we just create electrons in all possible states, minus infinity to mu2 or to mu1. And so here you see that you have this S of t, which was shown here. So it's tunneling, but basically you can calculate this S of t at long times, and you see that it becomes just these operators, the operators which connect psi plus epsilon, psi minus epsilon. So this is just a scattering operator at long times. So we know how it acts on non-interacting Fermi C. So it just entangled fermions. So it entangled fermions with via this relation. So we know how ST acts on the Fermi C. Okay. What we don't know how these operators F, the Klein factors, time-dependent Klein factors, and phi's, which are plasmon operators at this position. You don't know how to act on the transformed Fermi C because they're written in terms of plasmons. But then you can use the formula here. So this formula is very important. You can connect plasmon operators to fermion operators. So again, you know how to calculate action of phi operators on non-interacting Fermi C because there is a connection between plasmons and fermions. Then you still need a Klein factor, but then you know that due to this relation. So your Klein factor can be written in terms of fermionic operators again. So you, at the end of the day, you get this very simple formula. This non-interrupting fermion operator. These operators will be written in terms of fermions again, and this is just constant phase shift. Yes, so this final formula, you see that there will be phase shifts, and these are phase shift operators. Like that, so you see that they are represented by integral of electron density. This non-interrupting electron density. There is some kernel here, so there is an integral of electron density with this kernel. So all electrons are interacting inside, and this gives you phase shifts for these electrons which propagate. And then here, due to this S of t, which are tunneling matrices, you have to also transform operators. You need to transform these phase shift operators via S operators, which entangle fermions. So it's here. It's just matrices. These are just two matrices. These two matrices really work like so you have psi of epsilon alpha in the channel alpha is equal to S alpha beta psi beta of minus epsilon. So it's very simple transformation. And matrix S alpha beta is this one. R A of B or B minus IT A or B equals I alpha and then minus I T A or B minus I R. And this is a tunneling reflection of this is a non-interrupting fermion operators. And Z is a D minus VT, it's D1 minus VT and D2 minus VT. And Q will show you how Q looks like. So this Q operator is, can be written in terms of plasmon phase shifts. So it's sum of plasmon phase shifts with implicit phase operators. Everything is clear.
This thing that you said, I mean, you have one piece that is interactive. But then you put out a condition and you calculate the three one-dimensional purple systems, right?
Yes, sir.
I mean, you evaluate that in the non-interacting.
Yes.
And that's again one-dimensional.
Yes.
How did I see that in the original problem of the parameter? That was a good physical description.
So the H states are one-dimensional.
Yeah.
So there is a bulk, and the H states are one-dimensional on the size of the edges or the magnetic length.
But why are they interacting only in the region?
Why this model is good?
Yeah.
So I tried to explain that the interactions before the contact, they don't play any role because of power blocking. These interactions don't play any role because electrons are chiral. So all the current which propagated through the contact, it's already there, so it can't come back. So you don't affect the current here by electrons here if there is no this interaction. So interaction between these two electrons or these two electrons is important, but it's usually screened by the contacts because there's a contact and there's a wall there and electron interaction near the contact usually is screened. So this is our model, and of course one should say why this model is okay.
So in that region you have both parameters?
No, in this region I have only one parameter. Yes, only one parameter. But electrons interact with long-range interactions.
Yeah.
So this electron will interact with this electron. If electrons interact with short-range interaction, it just normalize material velocity.
Yeah, that is just looking at it.
Exactly. Yes. Yes. But in this case, long-range interaction gives you phase shifts for plasmons, and these phase shifts are used in calculations.
So what's the path of the interaction?
Sorry?
Long range interaction.
Yes, it's cool. So, people in principle studied this, and they still don't know what are the interactions inside. They can be screened or partially screened. So we don't really know. This type of experiments can actually give you some insight for the interactions.
But which U are you using? Your U of X subscribe?
I'll show you different use.
Okay.
So I wrote this formula. Some of the formulas are written. So for example, this one is written for constant interactions. So there is a G, which is interaction strength, T is the length of the arms. So this is just for constant interactions, because then you can obtain some analytical formula. But if you don't have constant interactions, you have long range coordinates, so you need to solve Bogoliubov equations. And this, I'll show the numerical results for it. I mean, numerical in the sense of calculation of some determinants, simulation. So this decoupling of contacts from the interactions really allows you to write this G12 in terms of only non-interacting fermions, which are modified by some phase shift operators, which in turn can be written also as non-interacting fermions is multiplied by some kernel. And this you can show exactly. So you can start with non-interacting quantum wires, then you can switch on interaction and tunneling T is equal to 0, and then you'll see that you'll get some integrals. In these integrals, there will be some pole structure, and you'll see that there will be contribution from e to the ikx plus I delta, and then there will be contribution which will decay with time. So there will be imaginary poles, and this gives you contribution which at T is equal to 0 turns 0, but then it decays with time. And if you take it at long enough times, you see that this contribution is very small. So what is left is just e to the ikx minus I delta. It's like you can in principle start from some stationary scattering problem if you want. You don't need to switch on interactions and so on, but to prove it rigorously, you need the switching on mechanism. I mean, probably because it's a matter of how they present it in a better way. But so in principle, one can start from stationary scattering problem and nothing is the result. In the stationary scattering problem, you'll get just this formula. Yeah, so just to show you these phase shifts for electrons, for plasmons, and these phase shifts are shown for this potential. So if you have finite range interactions, and the range of the interactions is very small, you just have this broad feature, and when the range of the interactions become large, here, for example, the range of the interaction is larger than the length of the arms, which is another parameter. Then you have this type of interesting feature, which plays a role probably in creating this zero source of visibility. Although I can't say directly.
What's omega? Sorry, maybe I missed it, but what is omega?
Omega is the energy of the plasma, or momentum.
Yeah, okay.
Because momentum is omega divided by K. Also by defect.
I'm sorry, I guess I missed it simply. How is it related to the different chemical potentials?
It doesn't. It's not related to it.
Oh, okay. So what I'm looking at is not really the oscillation.
These are plasmon phase shifts. These are just plasmon phase shifts, just to show how they look like. And this is kernel. So for constant interactions, when interactions are just U inside the interferometer. So it's U multiplied with integral rho of x. Here is so it's gamma parameter which describes the strength of the interaction. So this gamma, it's a dimensional parameter. It's GD divided by 2p h bar. So it's basically related to the phase shifts which is described before. G is the interaction strength, D is the length of the arms, and is divided by D. So you see it appears here. G naught is a function which is as a basic function, it's sine x divided by x. Okay. So you see here this polarization temperature sine x over x squared. Here's a picture of the kernel in real space. So we see that electrons interact. So electrons interact. And this kernel couples electron inside the interferometer. So there's electron inside the interferometer. It couples to all electrons inside, and it also couples to electrons outside, which is shown in this feature here. But this interaction decays with distance between electrons. This triangle is a triangle from the calculation of Nether, this paper I mentioned before, which, so in his approximation, this kernel doesn't have this form, which we obtained exactly, but it rather has this very simple triangular shape form. And if you calculate visibility for his kernel, you get this picture which I explained later. So here you see that small interaction gives you this picture, and larger interaction give you peculiar oscillations for the kernel.
Sorry, the dashed line is also for Nether?
No. So here on this picture, it's our calculation.
It's
So
for
there is only one
I see, he has
picture.
only the bigger.
Yes, he has different depending on the interaction, but it just scales. But it's always triangle. There is no features like this. Yeah. So this is just a picture of real space of this kernel. And so in his calculation, he didn't do calculations exactly. So he approximated. He did approximation for density operator, and he took. So now I just need to remember. So I don't remember. If somebody is interested, I can tell you later which approximation he did. But if you calculate it exactly without his approximations, you will see that you have decreasing visibility at 0 bytes, which is quite unphysical. And this is because one of the important parts of his approximation was that, or rather I should say that it's the same as if you would consider only finite band of electrons. So if you consider electrons from K minimum to K maximum. It's very important in this problem, it's very important to have infinitely filled Fermi, otherwise electrons can scatter from this K to this K, so they can go down to arbitrary energies, because they can decrease energy just by scattering. And there is no ground state for this problem. And it's very well known, it was shown by Lieb and Matisse. This gives you this decreasing visibility at K is equal to 0, or at energy is equal to 0. So this chemical potential difference or voltage and this visibility. So our calculation is shown here. So if you take exact kernel and you calculate these matrix elements, and I will show later how to calculate these matrix elements with free fermions. So this free fermi C, free fermion. Again, this matrix is also free, dependent free fermions. So I mean, these are Schrödinger operators, Schrödinger fermion operators. So here is voltage multiplied by the length of the arms divided by 2pH bar the Fermi. It's again the same parameter which you had here, and here is visibility. So it always starts from 1, and then it has a sort of plateau here, and then it decays, reappears, decays. And these are pictures for different interaction strengths. This particular picture and this picture is for constant interaction. I will show later for other type of interactions. So here you see that for small interactions you see visibility behaves like that. So there is a period depending on the interaction, and then you increase the interactions and period becomes smaller. And when interactions are very strong, then period doesn't depend anymore on interactions and becomes universal. So this is for very strong interactions, and it doesn't depend on interactions anymore. And here you see the phase shift. So here we've taken different lengths of the arms. So there is a D1 and D2, and there is some finite difference between D1 and D2. And for non-interacting picture, as I mentioned before, it should be linear. So the phase shift, so the phase of the Aronoff-Bohm oscillation should be linear with voltage. And then when you increase the interaction strength, you see that phase develops this type of picture, and it develops steps. And again, at very large interactions, this picture becomes universal again, and the steps don't depend anymore on increasing interactions further. So this for very strong interactions, so just steps in visibility, and it's just for comparison with experiment by Andrew. So this picture is visibility for finite range interactions. You see a very similar picture, so it doesn't really depend on what type of interactions you take. Just some features like periods of these oscillations at small interaction strengths will depend. But again, for very strong interactions, this will be universal curve. And this visibility for Coulomb interaction, you can see interesting features. here sometimes visibility can be larger than 1, and it's probably difficult to explain on a two-particle picture, but in principle one can expect this type of picture, and it was shown also observed in paper by Chalker.
What does it really mean? If it's bigger than 1, does it mean that in some peak more electrons would be present than in the others less?
It just shows that it's very sensitive to a change in voltage. So you change it a little bit, but due to the interference effects, the change of the current becomes very large.
But there must be some conservation law.
There is a conservation law.
So if you sum up all these peaks, you find that...
no, the current is conserved, of course, but there is an interference, yes.
Right.
The interference gives you this resonant type of behavior. You change the voltage a little bit, but then it goes off resonance and it gives you a very strong peak. Unfortunately, I can't explain in a two-particle picture. Probably one has to add more particles, but at least our calculation, this exact calculation gives this picture.
But there must be some conditions on the interaction, because if you have an interaction, so just looking at the liquid, then you said you can just rewrite it as a free
Non-interacting
non-interacting fermions with just normalized parameters. So what current? But you said here that will constant.
For appearance of the peaks, you just need fine range interactions. Any interactions which is larger than 0 range will give you oscillations, but the period of oscillations will depend on the range of the interactions, of course.
Yeah, but Coulomb has no range.
There is intrinsic range here because there is a cutoff by these two contacts. So we always have a cutoff here.
Okay.
But as I say, it doesn't really depend on what type of interaction you take. You can take interactions which are smaller in range here, smaller than cutoff. So interactions. So if you have interactions acting in this region, then electrons like that will interact, but they don't feel the cutoff. You still have the region.
What's the dispersion for these flats?
It's linear dispersion, yes. So for very long times, it's linear dispersion is delta K. It depends again. So for plasmons with short-range interaction, for example, or Coulomb interactions, this dispersion will modify, and in principle you can calculate it also from Bogoliubov calculations.
But you will see these patterns even when you have linear dispersions.
Yes, what is important is ingredient is phase shift of plasmons rather than dispersion.
But you wouldn't see it if you had a linear dispersion.
No, you wouldn't see it when you have Luttinger liquid. So because Luttinger liquid you can again re-express in terms of fermions.
Yes, I know.
And yes. So you don't have any phase shift in this.
Sorry, what does it mean for visibility higher than 1?
As I say, it's I can't explain it in a very simple model, but
Just from the definition,
yes.
can it be higher than 1?
Yes, it can be higher than 1. But I don't have these formulas here. I can show you later. I have for calculation on just piece of paper. I'll show if I can be higher than 1. I just don't have it here, and I'm afraid that I will not be able to.
Well, you're asking for the definition.
Sorry?
What's the
What's the definition of visibility? I thought that it's one
So
for
definition,
device that is between full transmission and being completely closed.
The definition of visibility is nu is equal to Gmax minus Gmin divided by Gmax. So it's different in the maximum minus difference in the minimum divided by Gmaximum and Gminimum. So if Gmaximum and Gminimum plus Gminimum is very small, we can still divide it.
Well,
Yes, so it can have different signs as well. I should show you proper formulas. Let me just show it afterwards. Okay. I have it in this one. But the problem is that I can't explain it on a simple picture. So I can show how it appears.
No, if they have different signs, then
Because so G is so it have different it has effects. Yeah, so these are also some effects of asymmetries. Yes.
So it means that under certain conditions you can get negative differential conductance.
Yes.
Like in an amplifier.
Yes, as I say, there can be resonance. For example, for some particular points, you can have destructive interference, but when you go a little bit far from this point, it will explode because there's no condition for resonance. So this peculiar feature, and I can't explain you. I can show from the calculations that it appears. I can show how it can appear also in this formula. Just now, I'm afraid that I'll make a mistake in showing you. I can do it later. And I don't know how to explain it on very simple terminal. So this I don't. Okay, so these are effects of asymmetries. You can have different lengths of the arms, and then you have different channeling in the contacts. And you see that if the lengths of the arms are different, and then interaction, if the interactions are small, then you have this type of without a minimum of the visibility. But then when interactions are strong, then there will be again minimum of the visibility, dependent on the difference in the length of the arms. And for strong interactions, you see that there will be always steps like that, rather than linear behavior. Yes, and probably should finish, but this way how to calculate matrix size is pretty Fermi. If you have some Fermi here and Fermi here, and have some Fermi operators here, there is a place, you just need to put unitary operators here. You write your Fermi C as a product of creation operators acting in a vacuum, then you put e to the IH here, and so you can write it as there is some determinant, it's an inverse of a matrix which is made of e to the IH, matrix elements of e to the IH in the states which are filled with elements. So you can calculate it numerically. And if you take a large enough matrices, then the result will converge, and you observe it for, say, 500 particles in every channel. So these are in summary. Interesting application could be to do similar calculation for fractional quantum Hall effect with interferometry, because we know how to solve the problem for single contact dependent interactions as well in the interferometry. But I'm not sure that one can solve it exactly. Probably there's some. Thank you very much for your attention.
Any further questions about the attack? In reality, how many electrons is there in the Fermi C? The physical system.
How many in the Fermi C, I don't know, but they can have one extra electron inside the interferometer, so they can vary it a little bit and have one extra electron.
Bosonization is sort of formally dependent.
Bosonization depends on the infinitely field Fermi C case, but there is experimental evidence that bosonization describes the existence very well.
So, in your visibility plots, apart from the fact that it goes above 1, you always seem to have this plateau at 1, which is not present in the experiments.
Yes.
Any clue what is in
plateau, you mean this plateau?
Yeah.
Yeah, in experiments it's a little bit different, but yes, I don't have any maybe this effect of interactions between electrons here and here. Yeah, I don't know how does it correspond to experiment. So in experiment you see we have this type of behavior. There is no plateau. But in our calculations we always see plateau. So probably we need to include interactions between electrons here and here.
But you could attach the curve that looked more like this, right?
Uh,
Can you get that? Yeah.
Not really. There's always
It's not really lower. Yeah.
there's always plateau here. So it's behaves like almost non-interacting first and then is increasing voltage goes down. But we don't observe in all the calculations. We never observed different